Okay, so today we are going to start a new chapter, chapter 6 on limits of sequences. So in this first section we are going to see convergence of sequences and limit laws of sequences. So these are some beginning words from the author. In the previous chapter we defined the real numbers as formal limits. So let us recall what we did. We defined real numbers as formal limits of Cauchy sequences of rational numbers, and then we defined various operations on the real numbers. However, unlike our work in constructing the integers and rationals, we never really finished the job of constructing the real numbers, because when we constructed the integers, we defined integers as formal differences of natural numbers. But at some point, we replaced those formal differences with actual differences, namely after defining actual difference. Just like that, when we defined rational numbers as formal quotients of integers, then after developing the theory, at one stage where we defined actual quotients, formal quotients were replaced with actual quotients. We have so far not done anything like that for real numbers. We never fully finished the job of constructing the real numbers because we never got around replacing formal limits with actual limits. In fact, we haven't even defined what actual limits are. So that's what we are going to do in this section. And in this chapter we will study sequences of real numbers and their convergence or lack thereof. So the first definition is just that. In fact, in order to get to the definitions that we already came across in rational numbers, namely Cauchy sequences, convergence and those things, we are going to follow the same path by repeating many of the machinery, for example epsilon closeness, eventual epsilon closeness. Those things we are again going to do here, but now we will be doing them for real numbers. That time we did them for rational numbers. So the first definition in this direction is this. Definition 611, distance between two real numbers. You will see that all these definitions are exactly similar to the corresponding ones for rational numbers. So the definition is just this: given to real numbers x and y, the distance between x and y denoted by our usual notation dx comma y is defined as this absolute value of the difference x minus y. And recall that the same thing we did for rational numbers. when x and y are rationals, then the distance between x and y is defined by that same formula. We saw it back then when we defined those things for rational numbers. So that's why clearly this definition is consistent with that definition. What was it? What was the number? Definition 432, which defines the distance between two rational numbers. Further, proposition 433, which has properties, elementary properties of this distance between two rational numbers, also continues to be true if we replace all the rational numbers by real numbers. Works just as well for real numbers as it does for rational numbers. So that thing is there, and the reason is that because the real numbers obey the same rules of algebra as the rational numbers. So, which is very easy to understand. The rational numbers form a field, the real numbers also form a field, and as far as the order relations are concerned, their properties also are similar, except for that one property, of course. The real numbers satisfy, the system of real numbers satisfies the least upper bound property, which the rational number system does not do. However, that's not what we are talking about here. We are just simply talking about these things. So these are the same for real numbers. So because we defined the distance between two real numbers just like how we defined the distance between two rational numbers, so all the statements involving that distance function that we came across in proposition 433 continue to be true if we replace all the rational numbers by real numbers. Okay, now next, now that we have defined distance between two real numbers, so we can now define epsilon closeness. So that is the next definition. Epsilon close real numbers. Let epsilon greater than 0 be a real number. Two real numbers x and y are said to be epsilon close to each other if the distance between them is at most epsilon, that is if this inequality is true for x and y, then we say that just like before, x and y are epsilon close to each other. Other ways of saying this is that x is epsilon close to y or y is epsilon close to x, same thing. Again, it is clear that this definition is consistent with the definition of epsilon closeness between two rational numbers, which is definition 434. Okay, now some words, some things about sequences of real numbers. In fact, let us just consider this notion. We are considering it for the first time because so far we have only seen sequences of rational numbers. Now we are going to transition to sequences of real numbers. Now let an the notions related to these sequences, the notations used to denote these sequences are just like what we had for rational numbers. But now whatever we are doing, we are going to do for real numbers. Let this be a sequence of real numbers, that is, we assign a real number an for each integer n greater than or equal to m. So a sequence of real numbers is really after all a function which assigns to each integer n greater than or equal to m some real number. The starting index m is some integer. Now there are some things that need to be said about this starting index. Usually this will be 1. Usually this will be 1, but in some cases we will start the index from an integer other than 1. So the sequence we see here, such a sequence we can start from say 0 also, or maybe even -100 or 200. It depends on the situation, okay, and our convenience. We will see at one stage that although if we use a different index, if we use a different starting point from the conventional starting point of 1, then strictly speaking we get something different. If for example you have a sequence like this 1, 2, 3, etc., and you denote this sequence by an, where you start n from 1, and your definition is an equal to n, then clearly this is the sequence. However, if you choose to start the sequence from say 200, then this will not be the sequence. The sequence will now look like this. These are different sequences, but we will see that when we get to the notion of convergence and limit of a sequence, it will not really matter where we start. Okay, we will see these things. So that's why we have kept the provision of changing the starting index and not taking it all the time to be some fixed integer, say 1, it has to be 1. There is nothing like that, and there is no need for that also. The starting index can be any integer, that's the point, other than 1. One more thing is this: the choice of label used to index this sequence is unimportant. And the reason is this: the sequence AK, where k varies from say m to infinity, is the same as the sequence AN So whether we call this index k or n, it does not matter, because these are just some names given to a variable, dummy variable. So that's why that does not change anything. Okay, now the next thing is, having defined distance between two real numbers and epsilon closeness between two real numbers, it's now time for us to define Cauchy sequences of real numbers. So that's the next definition. And like before, we are going to first do it in stages. First we will define epsilon steadiness, then eventual epsilon steadiness, and finally Cauchy-ness. Okay, so 6, 1, 3. Cauchy sequence says of reals. Reals means real numbers. Let epsilon greater than 0 be real. A sequence an where n varies from n to infinity, where capital N is some integer, some chosen integer of real numbers is said to be epsilon steady. And these things are just like what we had before. Okay, recall that the same exactly similar definitions we had before when we defined Cauchy sequences of rational numbers. This is said to be epsilon steady if aj and ak are epsilon close for all integers j and k greater than or equal to n, that is so that is a sequence being epsilon steady. A sequence of real numbers. A sequence of real numbers sometimes is also loosely called a real sequence. A sequence of real numbers is said to be eventually epsilon steady if there exists an integer n greater than or equal to that index where things are starting, such that the sequence, this sequence where the index instead of now starting from m is not necessarily starting from m but from capital N. If this sequence is epsilon steady, if this happens, then we say that the original sequence is eventually epsilon steady, this one. And finally, a sequence this of real numbers is said to be a Cauchy sequence if it is eventually epsilon steady for every positive real number epsilon. Not elaborating more on this because we have already seen what these things really mean before for sequences of rational numbers. So you already know what these things mean. So let us now. So we have three things here in this definition. Real sequences that are epsilon steady, real sequences that are eventually epsilon steady, and real sequences that are Cauchy. So in steps we got to the notion of Cauchy sequence. Now we can combine all these things to write at once what a Cauchy sequence is without using these intermediate steps of epsilon steadiness or eventual epsilon steadiness. So to put it another way, so the definition ends here. A sequence an of real numbers is a Cauchy sequence if and only if for every real epsilon that is positive there exists an integer n which is at least n such that this distance between aj and ak is less than or equal to epsilon. If I am remembering correctly, the author has used n and n prime, but it does not matter because these are variable names. Less than or equal to epsilon for every integer j and k greater than or equal to n. So if this happens, then then of course the sequence is Cauchy, and if the sequence is Cauchy, then this condition is true. So it is writing all the things in detail without going like this. Same, it's another way of writing the same definition. And then again, these definitions we are saying because we have three things here, no? Epsilon steadiness, eventual epsilon steadiness, and Cauchiness. we had these same things for rational numbers also. So this definition is consistent with those definitions, are consistent with the corresponding definitions for rational numbers. And in fact, which are these definitions? Definitions 513, 516 and 518. Okay, but there is one more issue here. You see, although this definition of a Cauchy sequence of real numbers is just like the definition of a Cauchy sequence of rational numbers, but there is one thing, do you remember? In the definition of a Cauchy sequence of rational numbers, the epsilon we chose was rational, and now the epsilon we are choosing is real. That time we said that this distinction will not matter. Now it's time for us to actually show that it does not matter. So what we want to show is that, say we are given a Cauchy sequence of rational numbers according to the old definition. Then we are going to prove that it's also going to be a Cauchy sequence of rational numbers according to the new definition, where the epsilon we will choose is a real number. Conversely, if a sequence of rational numbers is Cauchy by the new definition, then it's also Cauchy by the old definition. So then the consistency of the two definitions will be complete. Okay, we will have completely shown, after showing this, that the two definitions are consistent. So that is the proposition. Next, proposition 614. Let an be a sequence of rational numbers starting at some integer index. Okay, that is understood, no? Then this is a Cauchy sequence in the sense of definition 5, oh, so that was definition 518. Then an is a Cauchy sequence in the sense of definition 518, if and only if it is a Cauchy sequence in the sense of definition, this new one, 613. Okay, so let us see the proof. One half of the proof is very easy. Namely, if you assume that the sequence is Cauchy in the sense of this definition, in the sense of the new definition, then it's Cauchy automatically in the sense of the old definition. So let us see that first. First, assume that this is a Cauchy sequence in the sense of definition 613. So let us write the definition. Then for any real number epsilon greater than 0, there exists an integer n greater than or equal to m such that the distance between aj and ak is less than or equal to epsilon for every choice of these integers j and k. The only restriction is that they have to be at least n. In particular, all these things are also going to happen if epsilon is chosen to be a rational number. Naturally, because this is true for all real epsilons, so in particular they are also true for all rational epsilon. In particular, for every rational number we are not again writing there exists an n, because there is an n, we have already chosen it. Okay, so n is already available to us. We have the distance between aj and ak less than or equal to epsilon for every j and k greater than or equal to n. But this condition, these inequalities are just what we have in the old definition, because the keep in mind that the original sequence is a sequence of rational numbers. Okay, so hence this is a Cauchy sequence in the sense of the old definition, that is definition 518. Okay, so 1/2 has been proved, which actually there is nothing to prove, it's just a matter of observing that it's true, that's all. Now conversely, let an be a Cauchy sequence. Okay, have we really mentioned that this is a sequence of rational? Yes, rational numbers. Okay, fine. This be a Cauchy sequence of, of rational numbers. We already know that. Now we need to say it's a Cauchy sequence in the sense of the old definition. Okay, let epsilon prime greater than 0 be a real number. For this epsilon prime, we need to show that there is an integer, say for example capital N prime greater than or equal to m, for which so and so things happen. And we have to somehow use the fact that the sequence is a Cauchy sequence according to the old definition. Okay, now I have the proposition number written here. By proposition 5414, there exists a rational number epsilon say double prime such that recall what this proposition is. This proposition says that between any two real numbers we can always find a rational number. If we have two real numbers x and y which are distinct and say x is less than y, then we can always find a rational number q that lies between x and y in this sense. So we have used that result here with 0 in place of x and epsilon prime in place of y, and the rational number q is denoted by epsilon double prime. Okay, now because epsilon double prime is a rational number and the sequence is Cauchy by the old definition, so we can apply the definition for this rational number. And note also that this rational number is after all a positive rational number. So let's write then there exists an integer n prime greater than or equal to m such that this absolute difference is less than or equal to this for every integers j and k greater than or equal to n prime. But now using this inequality we then get that other thing, but then this is also less than or equal to epsilon prime. Actually it will be strictly less than epsilon prime, but we can write that somewhat relaxed inequality. You cannot go the other way around. Okay, if this is given, then you cannot write strict inequality. From strict inequality you can go to this more relaxed inequality for obvious reason. I mean, you can see why. But then this is less than or equal to epsilon prime for every integers j and k greater than or equal to n prime. So that's what we wanted. Hence an is a Cauchy sequence in the sense of the new definition. New definition 613. So that completes the proof. Because of this proposition, we will no longer care about the distinction between these two definitions, of course. (518) and definition 613, and will view the concept of a Cauchy sequence as a single concept, unified. So this also shows one more thing. At least when we are dealing with sequences of rational numbers, if you want, you can choose the epsilon to be real. Rational instead of choosing real. There will be no difference ultimately. The Cauchiness of the sequence will not change. Okay, now we come to the even more important notion of convergence. So this is definition 615. Why is it 5? Oh, the proposition was 614. Convergence of sequences. Oh, this also has been done in steps. Okay, let epsilon greater than 0 be a real number and let capital L be a real number. A sequence an where the index is starting from n. Here, however, Tau has not written those things. Just simply a sequence of real numbers is said to be epsilon close to L if the distance between an and L is less than or equal to epsilon for all n greater than or equal to capital N. A sequence, it's just like that definition of Cauchy sequences. Here also there are 3 steps. A sequence an of real numbers is said to be eventually epsilon close to L if there exists an integer n greater than or equal to m such that the distance between an and L is less than or equal to epsilon for all integers n greater than or equal to okay. There is no need to write these things now, such that I should write it in terms of epsilon closeness, such that, see, that's what happens when we write something which is going on and on, then we get carried away. So it is a good idea to sometimes stop and see what we are doing, such that this sequence is epsilon close to L. And finally, a sequence of real numbers is said to converge to the real number L if it is, that means if the sequence is eventually epsilon close to L for every real number epsilon greater than 0. So then we say that the sequence converges to L. And just like the definition of a Cauchy sequence, one can unwrap these parts, that is epsilon closeness, eventual epsilon closeness, and then convergence, and write a single definition which does not have these steps. That one can do. One can unwrap. It's like unwrapping a Christmas gift. The definitions here and write the concept of convergence more directly. And for that we will see the second exercise at the end of this section. Let us now see one example. The sequence zero point 0.9, 0.99, then 3 nines, then 4 nines, and the terms go on like this without any end. This sequence is 0.1 close to 1. The distance between these terms of the sequence, between each term of the sequence and 1 is at most 0.1, and the largest distance is between this first term and 1, which is exactly equal to 0.1. The other differences are smaller, and it gets smaller and smaller. However, but the sequence is not 0.01 close to 1 because of the first term. The distance between 1 and 0.9 is 0.1, which is not less than 0.01. It's in fact greater than 0.01. However, the distances between the other terms and 1 are all less than or equal to 0.01, and the distance between this term and 1 is in fact exactly equal to 0.01. So this is because of the first term. So one can say that the sequence is eventually 0.01 close to 1. However, the sequence is eventually 0.01 close to 1. In fact, for every epsilon greater than 0, one can show that the sequence is eventually epsilon close to 1, and that's why it actually converges to 1. This can be shown. Epsilon close to 1, and hence converges to 1. Okay, so we have now defined what a sequence of real numbers converging to some real number means. Let us now see that the real number to which a sequence converges, if it converges at all, is unique. Whenever such a real number exists to which a sequence is converging, then it cannot converge to another real number. That real number is unique. So that is our next proposition. This is not always true. For real sequences it is true, but we will eventually come to a part of analysis, I should not say analysis, but a part of something, part of these type of studies where we discuss and study convergence. We will come across some places or some spaces, some systems in which a sequence may converge to more than one point. So the spaces where this type of things happen, they are typically not used in analysis because they are ill suited for the purposes of analysis, but they exist and they are studied in another area of mathematics called topology. We will see those things, okay, at some stage. So proposition 617, uniqueness of, what happened to my eyes? Uniqueness of limits. Let an be a real sequence. That means a sequence of real numbers starting at some integer. What is the need for writing this? Starting at some, we can see that here itself, no? M, and let L not equal to L prime be two distinct real numbers. Okay, we can again see the distinctness from here itself. Then it is not possible for the sequence to converge to L while simultaneously also converging to L prime. Okay, now we will prove this, and the proof naturally we will use a proof by contradiction type of strategy. Suppose an converges to both L and L prime. Okay, so that means an is convergent. Okay, yes, since L is not equal to L prime, the real number epsilon, which is the absolute value of L minus L prime divided by 3, is positive. L minus L prime is a non-zero real number. The absolute value of a non-zero real number is always positive. We already know these things from properties of absolute value, and we have divided it by 3. For y, that will be apparent pretty soon. Okay, now for this epsilon, we can now write the conditions for convergence of this sequence to both L and L prime. Since an converges to L, there exists an integer n1 greater than or equal to m, such that the distance between an and L is less than or equal to epsilon for all n greater than or equal to n1. Similarly, since the same sequence, according to our supposition, also converges to L prime, so for that same epsilon, in this case also we will get some integer which we are going to call, say, capital N2. There exists an integer N2 greater than or equal to m, such that the distance between an and L prime is less than or equal to epsilon for all n greater than or equal to n2. Okay, let k be the maximum of these two integers n1 and n2. Whatever the integers are, we don't know what they are because they are general. We only know that they exist, not what they are actually. But whatever the integers are, one of them will be the maximum. It may happen that they are equal or they may not be equal. In any case, there will be a maximum among the two, which will either be n1 or n2. That we are denoting by k. Then, since k being the maximum of n1 and n2 is greater than or equal to both of them. So k being greater than or equal to n1 and it is also greater than or equal to n2, so in the first set of inequalities, in place of small n, we can take capital K, because after all that is also an integer. We only need the integer to be greater than or equal to n1 in order for us to put the integer here. So we are now in a position to use capital K in place of small n. Here we have ak minus L less than or equal to epsilon, and just like that, since k is greater than or equal to n2, so here also in place of n we can put k. Doing that, we get the corresponding inequality ak minus L prime is less than or equal to epsilon. So now finally we have these two inequalities. Let us now use them. Hence, using, okay, we will use triangle inequality, but let us just first bring the term ak. This step is obvious because these two things cancel each other. Now we use the triangle inequality that we know is true for the absolute value function. This is less than or equal to L minus ak plus ak minus L prime. Since we have absolute value, we can write ak minus L in place of L minus ak plus ak minus L prime. Okay, and okay, now both of them are less than or equal to epsilon, so their sum is less than or equal to 2 epsilon. Now put the actual expression for epsilon. We get this. Since this is a non-zero, in fact this is a positive real number, we can divide on both sides of this inequality by that and get this less than or equal to, we didn't get any strict inequality, but it does not matter. In any case, we are going to get an absurd thing. This implies 1 is less than or equal to 2 by 3, a contradiction. This is impossible. So our the very first line where we supposed something that is false. So our supposition is false. That is, the sequence AN cannot simultaneously converge to L and L prime. So whenever it converges to something, that thing is unique. Okay, so now we know that the limits, so these are of course this number to which a sequence converges, whenever it converges, is known as the limit of the sequence, because now we know it is unique. It's not formal limit, it is another thing, it's another notion, it is actual limit. So now we are in a position to actually define limits. So this is the next definition, 618, limit subsequences. If a sequence of real numbers converges to some real number L, then that is known as the limit. If a sequence of real numbers converges to some real number L, then we say that L is the limit of the sequence. But what has tau written? Oh, okay. Then we say that the sequence, this is, we have to say that also, this is convergent. And that its limit is L. And just like formal limits, we are now going to use a notation to denote this number L. We write L equal to this to express this fact or to denote this fact. If our sequence AN does not converge to any real number, then an is said to be divergent. And in this case, we leave the symbol limit of an undefined. That is, in this case there is no meaning has been attached to it, and we won't use it. Note that proposition 617, that is uniqueness of limits, ensures that a sequence can have, sequence means sequence of real numbers, at most one limit. Thus, if the limit exists, then it is a unique real number, and otherwise it is undefined. Otherwise it stays undefined. Now there are some remarks about these things. The first remark: the notation does not indicate anything about the starting index of the sequence, or does not give any indication about the starting index M of the sequence. Of the sequence in question, but that is not relevant. At least as far as limits of sequences are concerned, the starting index does not matter. You can start at any point in the sequence itself. In other words, you can in fact neglect a few terms from the beginning, finitely many. We will see why that is so, but the starting index is irrelevant. We will see this in the third exercise. Thus, in the rest of this discussion, we shall not be too careful as to what this starting index is, or as to where the sequence starts. As we shall be mainly focused on the limits. So this is one thing. Another thing is this: we sometimes use the phrase xn tends to, or in fact an, because we are denoting it by an tends to x as n tends to infinity. That's how we read it. Okay, an tends to x as n tends to infinity to mean the same thing as this, as an alternate way of writing the statement that the sequence an converges to x. To mean this, we sometimes also write this phrase. But there is we have to exercise caution. Bear in mind though that the individual phrases, individual statements an tends to x and n tends to infinity, these are meaningless. Okay, we are not assigning any meaning to these statements individually. Only when they come together in this form, this means this. Do not have any rigorous meaning. Some people try to understand this as the statement n is approaching infinity. This statement itself, however, is not a mathematically rigorous statement, and there is in fact no need to make it rigorous, because we don't have any occasion where we have to consider just the fact that n is increasing without any bounds. This phrase is just a convention a very convenient and suggestive convention. Besides these things, there is one more remark. These remarks may not seem like much and may seem like too much ado about nothing, but they are important. If we don't have a clear idea of why these things are important, in the sense that you have to just go through them, you have to know that they exist for once and then you can forget, but you have to know for once. Remark: 6.1.10. The exact choice of the letter used to denote the index, or the name of the index. Which in our case is n, used to denote the index, which in this case is n. Is irrelevant. The phrase limit of ak as k tends to infinity has the same meaning as this. So whether we use k to denote the index or n to denote the index or something else, it does not matter. For instance, but why would one change the name from n to k? One situation where we are, I won't say forced, but it becomes convenient to change the name. sometimes it will be convenient to change n to k n to k does not mean literally n to k, but changing the name of the index to something else, because n may simultaneously be used to denote something else. So if you already have a situation where, say, you have the sequence an, where the general term is a suffix n, but that variable n, that name is available in the same situation somewhere else. Say n denotes something else, some number of elements in some set, then that n and this n, clearly they are different, but you may get confused. So that's why that is a situation where it's better to change the variable name in index name into something else, and we want to reduce confusion. And in this respect, we will see exercise 614. It will not be possible to complete all the results of this section in this video itself, but at least let us prove one more thing. Proposition 6.1.11. We now know what limits of sequences are, and we now know what convergent sequences are. So this is one limit. Limit of 1 over n as n approaches infinity is 0. Recall that we have already proved that this is a sequence of rational numbers, and we have already proved that this sequence is equivalent to the 0 sequence, where all the terms are 0, and as such both of them have the same formal limit. The formal limit of the 0 sequence is the rational number 0. So that's how we got the fact that the formal limit of this sequence is 0. But now we are going to show that the actual limit of this sequence is also 0. And this gives us an indication of how eventually we are going to replace actual limits, formal limits with actual limits. Anyway, let us see the proof. Let epsilon greater than 0 be any real number. by the Archimedean property there exists a positive integer n such that n is greater than 1 over epsilon. Actually, exactly how are we applying the Archimedean property here? Let us see. We have two real numbers, epsilon and 1, and in this case epsilon and 1 are both positive. So you can think of epsilon in place of x and 1 in place of y. So there is a positive real number n such that nx is greater than y. So like that we will get a positive real number n such that n epsilon is greater than 1. For such an n is greater than 1 by epsilon. I don't remember the exact proposition number or lemma number or whatever it was, Archimedean property. You can go back to that, and there you will see that we have the property and we are using that here. Then for any integer n greater than or equal to n, we have the distance between 1 by n and 0 is equal to 1 by n. N is greater than or equal to n, so 1 over n is less than or equal to 1 over n, and from this inequality we see that this is less than epsilon. So the sequence, we can directly write the sequence is convergent and its limit is 0, but for once let us use those terms, eventually epsilon close. So the sequence 1 over n is eventually epsilon close to 0. This implies limit of 1 over n is equal to 0. That's what we wanted to show. After this we have those discussions that we already did for sequences of rational numbers. Namely, if you remember, we proved at one point that Cauchy sequences of rational numbers are bounded, things like that. So all such things we will also do here for real sequences. For that, however, we need to first of all define boundedness of a sequence of real numbers. That we will do, and then we will also see that convergent sequences are Cauchy. The converse to that is a very important fact, and which that is the reason why real numbers have been constructed in the first place, that all Cauchy sequences of real numbers are also convergent. So these things we will see, and along with them we will see the limit laws, that if you perform algebra on convergent sequences, you get more convergent sequences. You add two convergent sequences, you get a convergent sequence whose limit turns out to be the sum of the limits of the original sequence. And one more thing I should mention is that we will do that thing where we were saying that we did not complete the construction of real numbers properly, that we did not replace the formal limits with actual limits. So that thing also is there, it will be done. So we will do all these things in the next part, next video. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.